Good morning, students. This is 26th lecture on digital signal processing and its applications. Today we shall study Z-transform. So Z-transform is an important tool in the analysis of signals and LTI systems. The Z-transform plays the same role in the analysis of discrete time signals or sequences as the Laplace transform does in the analysis of continuous time signals. And the question comes, why at all we take any transform, whether it is Fourier transform or Laplace transform or discrete time Fourier transform. The reason is the transform makes the analysis simpler. For example, if we convolve two signals in time domain, then the convolution of the two signals in other domain, that is Z transform or Fourier transform or Laplace transform, it transforms into the multiplication. And as we know, convolution operation is complex operation, whereas the multiplication operation is simpler one. Therefore, we can say this transform make the analysis of LTI system, that is linear time systems, easier. And today we are going to introduce Z transform for discrete time signals or sequences. So first we shall look at the definition of Z transform. So let Xn be a discrete time sequence. Discrete time sequence or discrete time signal. Its Z transform can be defined as follows. Can be defined as x of z equals summation over n running from minus infinity to plus infinity, x of n z to the power minus n, where this variable z is a complex variable. Let z be r e to the power j omega. So this is how we define the Z transform. The notation x of z or x of z represents the Z transform of the sequence xn. And for the sake of brevity, sometimes we denote x of z as follows. X of z equals, we use the capital Z and then we write Z transform in curly braces. So z of x of n. And this stands for Z transform of the sequence xn. It is to be noted that this xn is called inverse Z transform of xz. And one can use the following notation. X of n is the inverse Z transform of xz, or one can also say the xz is the Z transform of xz. Now it is to be important that since this x of z is a power series, this is a power series, Lagrange power series in variable z. Now if you expand this summation, you can very easily notice that the summation is nothing but x0, z to the power 0, x of 1, z to the power minus 1 plus x of 2 z to the power minus 2 and so on if you expand it in right direction. Similarly, if you expand it in left direction, you would be having x of minus 1 z to the power 1 plus x of minus 2 z to the power plus 2 plus x of minus 3 z to the power 3 and so on. So this is a power series. Now this power series may be convergent or may be non-convergent. So the existence of the Z transform, ZT is the abbreviation which I shall use for Z transform. So the existence of the Z transform depends upon the convergence of the series. If this series converges, then we say the Z transform exists. And if this series does not converge, then we say Z transform does not exist. Number two, this series is series in Z. Now it may happen that for some values of Z, the series may be convergent, and for some other values of Z, for a set of some other values of Z, this series may not be convergent. So what is the important that since Z transform is an infinite series, Z transform exists only for those values of Z for which series converges. In other words, I can say that this series, this power series, may converge for a set of values of Z, and it may not converge for another set of values of Z. And the set of values of Z for which this series will be converging, we shall calling this set of Z as the region of convergence. So the next important concept is the region of convergence. So what is the region of convergence? ROC, abbreviated as ROC. ROC means region of convergence. So what is region of convergence? So the region of convergence of XZ is the set of all values of Z. It is the set of all values of Z for which x of Z attains a finite value. So the values of z, or the set of values of z for which exist, or for which this series is converging, we call that set or that reason of convergence of xz. So now we shall take some examples, and through examples we shall see what is the Z transform, how we can compute the Z transform of a sequence, and what is the reason of convergence of that sequence, that we will see through example. Now it is important to note that whenever it is asked to you to find Z transform, it means that you have to find the expression of Z transform xz along with the reason of convergence. So reason of convergence must be mentioned explicitly whenever you are asked to find the Z transform. Let us take a simple example. Xn is a discrete time sequence, very simple sequence, 1, 2, 3. This is a 3-point sequence, and the first sample is corresponding to n equals 0. If 2 is corresponding to n equals 1, and 3 is corresponding n equals 3. If I draw this sequence, you can draw this sequence. This is n axis. So at 0, the sequence is 1. At 1, sequence is 2. And at 2, the sequence is 3. And elsewhere, the sequence is 0. And you are asked to find the Z transform of this. Now, as we have seen that xz is defined as the summation running over n from minus infinity to plus infinity, x of n, z to the power minus n. Now, since sequence is non-zero, only between 0 and 2, therefore, this summation boils down to the following. The limits would be now between 0 to 2, because elsewhere xn is 0. So if you expand this summation, you get x of 0, z to the 0, plus x of 1, z to the minus 1, plus x of 2, and z to the power minus 2. Now, from this sequence, or from this graph, it is clear that x of 0 is 1. So I can write 1 plus 2 z to the power minus 1 plus 3 z to the power minus 2. This is the expression for the Z transform of the sequence 1, 2, 3. But we have yet not mentioned what is the ROC. What is the reason of convergence? Is there any possibility that this sequence may diverge, or it is always converging? Now we know Z is a complex variable, r e to the power j omega. Now if this Z tends to 0, then what will happen? If this Z tends to 0, means r is tending to 0, then this term will become what? Infinite, because, or this term will also become infinite. So when this series is converging, for all the values of Z except the one value, that is Z equals 0, or in other words, when r equals to 0. So we can say the ROC is what? The ROC is the entire Z plane. Entire Z plane except one point. Except except what is that point? That point is z equals 0. So this series xz equals 1 plus 2z inverse plus 3z to the power minus 2. This is always finite except at the point z equals 0. Now, if you take another sequence, let's say the sequence is the following. Xn equals, again the sample values are the same, but the location of arrow has been changed. Now I have placed arrow here, which means the sample value 3 is corresponding to n equals 0. This value is corresponding to n equals minus 1, and this value is corresponding to n equals minus 2. Now if I ask you to find the Z transform of this sequence, again from the definition, x of z is summation over n running from minus infinity to plus infinity, x of n z to the power minus n. But this time our sequence is non-zero only between minus 2 to 0. Therefore, this summation would be from n running from minus 2 to 0, x of n z to the power minus n. And if you expand this summation, you will get x of minus 2 z to the power 2, x of minus 1 z to the power 1 plus x of 0 z to the power 0. And what are the values of x of minus 2, x of minus 1, x of 0? They are 1, 2, 3 respectively. So you can say x of z is z squared plus 2z plus 3. So this is the expression for the Z transform. But again, the question is, what is the reason of convergence? This series, this is the question, does this series converge for all the values of Z? Naturally, the answer is no. If this Z is tending towards infinity, then this term and this term will tend to infinity, and therefore for Z tending to infinity, this series is diverging. So what is the ROC? What is the reason of convergence? Reason of convergence is entire Z plane except Z tending to infinity. Now, if I take one more simple example where the sample values are the same as before we have taken in the previous two examples. Let's say xn is, let xn be 1, 2, 3. But this time I have placed arrow here. This means that this sample value 2 is corresponding to n equals 0. This sample value is corresponding to minus 1. And this sample value is corresponding to 1. And if we find the Z transform of this sequence, this time I am writing it directly. It would be what? It would be Z plus 2 plus 3 Z to the power minus 1. Now again, this is a series, though it is not infinite series, it has 3 terms, but we can see that this series will not converge for 2 values of Z. One value of Z is Z equals 0. If Z is tending to 0, if Z equals 0, then this term will become infinite. And if Z is tending toward infinity, this term will become infinite. So what is the ROC? So ROC is entire Z plane except 2 points, except Z equals 0 and z tending to 0. So what we can conclude from these three simple examples? It is easily seen that the ROC, what is the conclusion? Conclusion is the following. ROC of a finite duration sequence is the entire Z plane except possibly the points Z equals 0, Z tending to 0, or both. Both means Z equals to 0 and Z tending to infinity. So in the first example, we saw the point which was excluded from ROC was Z tending to infinity. In the second example, we saw the point which was excluded from the ROC was Z equals 0. And in the last example, we saw the ROC was entire Z plane except these 2 points, Z equals 0 and Z tending to infinity. Now we shall discuss the Z transform of infinite duration sequence. And then there we will see that it is not necessary for infinite duration sequences that the Z transform is the entire Z plane. That we will take in the next lecture. Thank you very much.